I'll begin this afternoon's session with a brief introduction. Welcome to the Canadian Institute of Forestry's National Electronic Lecture Program. My name is Sharon Young, and I will be hosting today's session. Today is Wednesday, December 11th, 2024, and this is the last session in the e-lecture series featuring graduate student research. For today's session, we are pleased to have Sohail Akram, who will give a presentation titled Assessing Forest Resilience to Disturbances in Interior and Northern BC. To kick things off, Sohail's research focuses on quantifying the resilience of BC forests to wildfire, drought, and insect outbreaks. This work integrates resilience frameworks and models to enhance forest management practices in the face of climate change. With that, I will now pass it over to Sohail.
So thank you very much to CIF to provide me this platform to show my research. And good morning to the people who are joining from Pacific time zone, and good afternoon the people who are joining from Eastern time zone. So today the presentation learning goal is to understand and apply the methods to measure the resistance capacity of different disturbance that is happening in across the Canada and especially in the BC, and then explore the relationship between different stand attribute like stand basal area, species composition, and stand age, how its effect on the disturbance resistance of different disturbance, and also identify or propose some kind of a management practice that can promote these disturbance resistance. At the same time, it's helpful to develop the emerging properties that can, overall enhancing the forest resilience and the productivity. And the second part or the last part, so this presentation have two parts. So the second part is more about to quantify the future and the projected drought resistance by using the simulation model that is FES BC version. So the part one research is like the conceptual framework behind this research, disturbance impact on forest ecosystem in Canada and also especially in BC. What are the objective for this research? What methodology we use to do this research, and then some result and the management application. The second part is about some introduction about growth and yield simulation model that is FES BC version. What is the future drought resilience and how it is vary across the time scale, and also some kind of a summary of these parts. And this is a kind of a simplest research framework. So firstly, we quantify the current resistance capacity of each disturbance that is coming from a different indicator that have an impact on a disturbance onset and spread. And the second part is to analyze the impact of different stand attribute on this disturbance resistance capacity. And the third part is how this resistance capacity and this relationship is helpful to helpful to develop and foster the emerging properties that is kind of a forest resilience, adaptive capacity, and enhanced productivity. So this is a kind of I would say a complex slide. So at the bottom, you see that we have a stand structure, and then we have a three attribute that is stand basal area, age, and species composition. And on the middle, we have a disturbance, wildfire, drought, mountain pine beetle, western spruce bird, spruce beetle. So these are the case of disturbance that we are studying. And then we have a forest management kind of a some kind of a harvesting thinning operation there, and then also plotting some broadleaf species in a monoculture stand. So, and then based on their interaction, we have some emerging properties like resistance, resilience, ecosystem services, adaptive capacity, and enhanced productivity. And when we have these emerging properties in our stand and how it's have a positive impact on the disturbance resistance and resilience based on the indicator like the host species basal area in terms of biotic disturbance, aspect, quadrant mean diameter again for the like mountain pine beetle, spruce beetle, canopy base height is important for the wildfire, the spread and onset. In the next few slides, I will explain like each part of this framework. So what is the disturbance? So the disturbance is an event that can change the distribution and abundance of any organism, leading to a change in the structure of an ecosystem. In our case, the disturbance in study is wildfire, drought, mountain pine beetle, western spruce beetle, budworm, and the spruce beetle. And what is the stand structure? So that is the size, quantity, and the arrangement of vegetation and the relative feature. And we know that disturbance impact on the stand structure shape, and stand structure is also important to the onset and the spread of the specific disturbance. So what are the indicators? So the indicators that we use to quantify the disturbance resistance capacity. So those are the physical and the biotic component of a stand contribute to disturbance onset and spread. For example, the host species basal area for mountain pine beetle, for spruce beetle, also the spruce budworm, aspect for the western spruce budworm, quadrant mean diameter again for the mountain pine beetle, spruce beetle, and then we have a canopy base height and the topographic witness index that is important for a drought disturbance. So what is the emerging properties? So the emerging properties is the ecological properties that develop in a non-linear and often cross-scale manner in response to a variation in a temporal change or the first structure diversity change. So the indicator and the emerging properties, they are interlinked, and then they are further interlinked to a stand, the stand, overall stand structure, and also the disturbance onset. In the next few slides, I will further evaluate how they are interlinked to each other. So a few slides, what is the disturbance impact on here in Canada and also specifically in BC. So the first is the wildfire. We know that the wildfire event and also the wildfire intensity and the burn areas increasing almost every year, especially the last 10 or 12 year is very, very bad, especially for the BC wildfire area burn, evacuation, and all other, the linked things with the wildfire. The next is the drought. So we know that the damage by the drought to a forest area is also increasing, and that is not only in a current scenario. So you can see with a BC area survey in 2023, a huge amount of area was damaged by a drought. And then you have also one figure here that is on August 10 in 2023, where we have a kind of a very high intensity drought in BC, in major part of the BC. And then on the left side you have a projection of the drought, what would be happen in terms of precipitation in coming year with the different carbon dioxide emission. And if we see on the BC especially, so the amount of precipitation is decreasing across a different time scale. And this is about our biotic disturbance, especially the mountain pine beetle and the spruce beetle. So we know that we have a kind of a pandemic situation of mountain pine beetle in BC in 2000 and that time of period. Although the risk, the current damage from mountain pine beetle is lower, but there is our main constant threat of mountain pine beetle outbreak as well. The other is the spruce beetle. We can see the trend is increasing, and here we have a different, the color with the different province. And if you see, especially for the spruce beetle, the British Columbia is top across all other provinces in terms of spruce beetle damage. And this is the western spruce burn. And we also in Canada, we have a eastern spruce burn, we have a western spruce burn. So that is also a kind of a growing threat to interior and the northern BC boreal forest that need to be studied. So by studying the relationship between stand structure, disturbance resistance capacity, and emerging properties, we can develop a comprehensive forest management plan that can ensure the long-term health and the functionality of the forest ecosystem. So this is very important. Like just the quantifying the disturbance resistance is not only important, but to understand the relationship between disturbance resistance, between disturbance and the stand structure and the emerging properties is very, very important to make a future management plan to modify our forest stand. And this is a kind of a specific objective for this study. So what is the current resistance capacity to biotic and abiotic disturbance in interior northern BC forest? And then the second part is do the basal area, age, and species composition and their interaction influence fire, drought, and biotic disturbance resistance capacity? And does their influence vary across a different back zone? So the back zone uh, is based on a different vegetation community, and then it's also linked with the climate and the precipitation and the site productivity tree. So based on these four criteria, in BC we have a different back zone. And then the third part is what is the interaction between our different disturbance resistance capacity, and how this interaction is affect on ecology recovery and the development of the emerging properties. So the data set that I use to analyze and run this framework is from the Prince George timber supply area that is collected by the Ministry of Forestry. So they have a permanent sampling plot. So I have a different kind of a multiple, the inventory in a few plots. So they are collecting like the earliest maybe in 2000, and then it's go from 2000 to 2018 with multiple inventories of the few plots or the new inventory of the most of the plots. And total number of the plot is 1339, and the most dominant zone. So we have here a different actually the total seven back zone in study area, but the most dominant is SPS, that is the subboreal spruce zone, and then the second is the Engelmann spruce subalpine fir zone. So these both zone actually make above 95% of this PSP data. And here you have the species composition in each like back zone. So in SBS is dominant with the subalpine fir and the lodgepole pine, and then we also have some component of Douglas fir and the broadleaf aspen and the poplar. On the other side, the ESSF is majorly mainly dominant by the subalpine fir with a subcomponent of spruce and the lodgepole pine, and also some elder and the hemlock. So we develop a framework to quantify the resistance capacity of each disturbance. And how we do it, we choose a four indicator for each disturbance that are important in disturbance onset and spread. And then we make an aggregate resistance score of disturbance that is the sum of all indicator with equal weightage. And here is the example of one like a wildfire resistance capacity. That is the sum of CFL, that is canopy fuel load, and then CPD, that is canopy bulk density, CBH is canopy base height, and then we have a resistance for US PH, that is understory per hectare. Here I will explain actually what is the importance of these indicator and why we choose indicator with just one example focusing on a wildfire. So start with the canopy crown fuel, that is the canopy fuel load and the canopy bulk density. So we know that under a kind of a moderate climate weather condition on that specific day when we have a fire event, if there is a huge or the large amount of canopy fuel load and canopy bulk density available in a stand, there is a high likelihood that a fire can become the big fire or worst fire and can burn maybe a major part of the landscape. And the canopy base height is very very important to the vertical movement of the fire from ground to the canopy. Like if we have a ground fire, like we know that the fire is a part of the forest ecosystem, we cannot eliminate the fire from the forest ecosystem. What we can do, like we can make a kind of a forest structure that maybe promote or helpful for a ground fire, but we have to make a forest tank structure in this in a kind way that it should not develop a crown fire, a big fire. So the canopy base height is a very, very important attribute to make a ground fire to a crown fire. And then we have an understory fuel stump per hectare, that is the woody material that is less than 7.5 centimeter dBH. So those are the important to start any ground fire. So if there is enough material, there is more understory woody material is there, ground fire will start. And if there is a lower canopy base height, that fire will travel to the crown. And if there is a huge amount of the crown fuel in terms of canopy bulk fuel density and canopy fuel load, so there is a highly likelihood that that fire become a big fire and it can burn up a major part of the landscape. and how we change this equation, or how we change this indicator into a resilience or resistance capacity or the resilience function equation. So that is based on literature. That is the first thing. So we have a one maximum value in terms of canopy base height. If the canopy base height, the stand canopy base height is more than 7 meters, so it means that there is a low likelihood that a fire from ground to go a ground fire. So its resistance capacity is one. And if it is less than 3, so there is a high likelihood that a fire from ground can go to the ground. So its resistance capacity is 0. And then we have a linear reduction from 3 to 7. So as we increase the canopy base height from 3 to 7, so the resilience is increased 0 to 1. So this is the resilience or the resistance function for each indicator. You can see a canopy bulk density, canopy fuel load, and the understory stump per hectare. How we define this value is from this reference. So this reference is actually tell us what was happened when a fire occurred on a specific landscape in a moderate climate condition. So these equation or these value is considering a moderate weather condition, not an extreme weather condition. Okay, so just here I did not mention the equation, but just mention the indicator that I use to quantify the resistance capacity of other four disturbance. For drought, use a site index and the basal area as a competition factor. Site index is a kind of the growth potential. And if a forest is growing on a high growth and a good soil productivity site, there is a highly chance that that forest or the species can cope with the drought. And then we have a topographer's witness index that is something linked with the accumulation of the water in a specific area, in a specific like a 1 meter cell. And then we are also use a drought risk assessment tool that is also the part of the second part of this presentation. This is the BC Ministry of Forestry drought risk assessment tool. They have a AET and PET value for like a 2020 and also for the future. And based on this value, they give a risk score to each species in each back zone. And we change that risk score into our resilience score. In terms of our biotech disturbance, especially for mountain pine beetle, the coordinate mean diameter of host species is very, very important. We know that if there is not, the enough sap flow or a thick phloem, it is, very difficult for a beetle to survive. So coordinate mean diameter, age is again very important. Stem density of the host species or the overall stand in terms of competition is very important. And then also the percentage of the host pine basal area, like the host species basal area in a stand is very important. So this is similar for the spruce beetle and the western spruce budworm. So what is the first step of the methodology is to identify the indicator, identify their resistance equation, identifying their score. The next step is when we have the resistance capacity a score for each disturbance. So then we test a linear model and we see that how three stand attribute and their interaction have influence on these disturbance resistance score. And then we define the species composition as a percentage of conifer basal area in a stand. And then we also see what is the correlationship between these disturbance resistance and on the first part, when we see that how these three stand attribute is important, have an influence on the disturbance resistance, we also evaluate in a different back zone if their impact is similar in all the back zone or there is any difference in a different back zone. So this is the first result. So what is the current resistance capacity of Prince George timber supply area for all these five disturbances? So we see that here high resilient mean that when the stand have a score more than 3, so the total score is 4 for each disturbance resistance, and when the score is more than 3, so that is high resistance. 1.5 to 3 between this is the moderate, and then lower than 1.5 is the low. And we see that if we just exclude the mountain pine beetle, all other disturbances they have a moderate to low resistance capacity with our current management or with our current stand structure. So and that is also we can observe what is happening on the landscape, especially in terms of wildfire. There is a huge wildfire, the season almost in last 5 or 6 year in BC, and this is something we can also see the based on this result, what is happening in the landscape practically, or what we are seeing in the landscape, and what our research is telling us is the whole landscape or the whole, the PG, PSP plot, they have a moderate to low resistance capacity of all the disturbance, just except for the mountain pine beetle. Okay, this is a little bit complex figure, and this shows on the x-axis you can see what is the current basal area distribution of this PSP plot, and on the y-axis you can see the disturbance resistance score. So is a wildfire here and the drought here, and we see that as the basal area increase in the stand, so this basal area is the total stand basal area. So resistance capacity decrease. And when we see in terms of broadleaf PA dominant stand, so if there is a more than 80% broadleaf PA basal area, and if we see those stand, so especially in the wildfire scenario, we see that as the base broadleaf component increase or their basal area increase in a stand, the wildfire that stand show high resistance capacity to the wildfire. Almost this is also happening same with a drought. The only thing is that we have a very few stand in the PSP that actually have a more than 80% broadleaf basal area, but most of the stand they are showing a high resistance capacity for wildfire and drought. And the other point is here that the basal area category 20 to 40 meter square per hectare is very, very important for management, because this is the two reason here. The one is this is the most dominant in PSP, like in PG PSP plot. And the second thing is that this is the category where we have actually the lowest resistance for all other disturbance. You can see on the next slide for the mountain pine beetle and the spruce beetle as well. So this is about the spruce beetle and the mountain pine beetle. As so here the species composition is not based on the conifer or the broadleaf, is based on the host species and the non-host species. So the one thing is clear, as the host species basal area increase in the plot, the resistance capacity of that disturbance decrease. And so this is also important when we think in terms of management, when we modify our stand. So how much the proportional basal area, or how much in terms of percentage of a host species component should be in the stand as compared to the overall basal area of that stand. This is the second result, that is something linked with effect size. So you can see on the x-axis that is effect size. So the effect size means that how much variance is explained to a specific stand attribute, or their interaction is here as well in this linear model. So we see that basal area that have a largest effect size on all disturbance resistance capacity. So we have, like on the right x-axis we have different disturbance. On the left y-axis we have all these basal area age, percentage of conifer species basal area and their interaction. And then we have this graph, and we show that the first one is a basal area, and basal area is actually the stand basal area is showing highest effect size. Is mean that stand basal area is showing explaining the more variance for all disturbance resistance capacity. Stand age is important for spruce beetle and drought, and then the species important, like a second important for wildfire resistance. So if we see in terms of management, what is important here, if we want to modify, or if we want to increase the stand disturbance resistance capacity, so that is basal area, and especially for all the disturbance, and followed by the age for spruce beetle and drought, and the proportional basal area of conifer species for wildfire. And this is the difference among different backzone. So you can see the A and the B panel. A panel is a similar, but is the we have differentiate based on SBS and ESSF. So SBS subboreal spruce zone, and ESS is Engelmann spruce and the subalpine fir dominant zone. And then we have a delta value. So the delta value is SBS minus ESSF for each this stand attribute effect size. If there is a positive value, so it means that it's most important in SBS. So most values is explained in SBS. And if it is in negative, so it means that that stand attribute have a more variance explained in ESSF. So we see that the basal area is the delta value for the basal area is more important for drought, wildfire, and mountain pine beetle in ESSF. And the stand age show more important for spruce beetle and wildfire in subboreal spruce, that is SBS zone. So the effect size or the variance explained by these three stand attribute and their interaction is actually changing across the back zone. And that makes sense because each back zone have a different species composition, and it's have a different, the disturbance risk or the resistance capacity there. And that is the last part of the result. And this is some kind of when we think about emerging properties, or when we think how these disturbances are actually interlinked with each other. So we see that the drought resistance capacity was positively low to moderate correlated with spruce beetle and the wildfire resistance. And there is a lot of study actually that make a link between drought and the wildfire resistance specifically. But we evaluate that there is a positively that is a kind of a low to moderate, like we have a zero point 0.2 or a 0.33 in some cases. So that is low to moderate category. But these disturbance resistant capacity actually are interlinked with each other. And then the western spruce budworm was positively and again moderately correlated with spruce beetle resistance because they are sharing the host, the same host species. Okay, so this is a discussion and also the relationship with what is the current status, what is the current emerging property, and what is the current state of the PGPSP plots or the landscape, and what kind of a management we can do or we can propose that might have a positive impact on the disturbance resistant capacity. So what we have right now, we see in the figure and we evaluate the stand basal area is have a high influence or has have are a more important stand attribute, and how it's linked with emerging properties. We see that when we have a high basal area, we have a low resistance capacity. So what kind of a management we can do? We can do a thinning here. We can reduce the basal area overall, and then we can also target the conifer species because we know that we have a conifer dominant stand in PGPSP, and then we can also target the whole species where we have that specific disturbance race. So we can target there the whole species there, and then we can reduce a basal area. What would be emerge from there? So based on that one, we will see there would be a high resilience and the resistance of the stand. There will be a less basal area, there will be a less competition, and how it will have an impact on the indicator. For example, when we reduce a basal area, we are reducing the low canopy fuel load that have a positive impact on our wildfire disturbance resistance. We are we are promoting the resource. We are reducing the resource competition that have a positive impact on our drought resistance. And at the same time, when we are reducing basal area and target host species, there is a fewer and the less host species proportional basal area is there. We are increasing our biotic disturbance resistance capacity there. And this is the stand like a kind of a species composition. Here, what we see that we have a stand 90% of PGPSP, they are a they are a conifer dominant, or they are a monoculture. What kind of emerging properties we have? We have a low resistance capacity almost for all the all the disturbance. What kind of a management we can do? We can do a thinning there, we can do a harvesting and planning, we can adopt a the different retention, like for example retention harvesting there. We keep some the mature and the mother tree there, and then we can plant that stand with diverse species. that could be a conifer broadleaf conifer mix, that could be a just conifer broadleaf mix. So we can promote a species composition in the stand and how it will impact. So it will improve ecosystem services because ecosystem services is linked with the species. And when we have a diverse stand species there, there will be a more ecosystem services there, and there will be a high adaptive capacity there because each species behavior to face or tackle and then resistance or the resilience of a specific disturbance is different, and how it will impact on an indicator. So if we have a more broadleaf component in the stand, that definitely have a positive impact on the canopy base side. So we are actually reducing the risk of wildfire from it's going from ground to the ground. It's have a the different resources complementary effects. So the different species, different the soil horizon, different water uptake, and also the reduced competition for the light and all other things that is happening with a same species competition. And then if we have a more broadleaf component there, we have a low food availability for the beetle. So this is the third thing, that is the age. Like most of these PGPS people are, so they are even age or they are plantations, and we see that based on the one story similar age plantation. The current state is that they have a low resistance capacity for all disturbances. And then what we can do here, we can do a retention harvesting here, we can do a mixed plantation here, we can through with the thinning or the retention harvesting, we can develop a different age classes there, and also the distribution of the conifer and the broadleaf with a different age classes, a kind of a very diverse. I just put a figure here to see that how it will potentially look like, how it will affect on emergent properties. It will develop or it will foster the adaptive capacity of the stand, and how it will impact on the indicator. It will lower the canopy bulk density. We will divide the canopy layers in a different layers. So it will actually divide the fuel in a different the layers. And it's also, it's have a different range of ecological niche and the resources. And it's also have an impact on the lower quadrant mean diameter when we have a different age classes there. So the overall stand have a lower mean quadrant mean diameter based on different age and the tree behavior. So at the end, this is again, I bring this figure here so now you will understand what is the stand structure and what is three stand attribute, how its impact on a disturbance resistance capacity, how we can do a different kind of a forest management there, and how it will evolve, or we can actually not we can we can developing a process that can evolve our emerging properties. And these emerging properties that include resistance, resilience, ecosystem services, adaptive capacity, enhanced productivity. It have an positive impact on an indicator. And when we have the lower value for these indicators that have a directly relationship with a disturbance onset and spread, so we can make our stand more, more resilient, more resistance, and we can get a more productivity there. So these are some kind of a management implication or a summary. So the Prince George timber supply area plots show moderate to low resistance capacity with their current management planning. Basal area emerge as a most important stand attribute for all disturbance resistance capacity. Stand attributes significant to manipulate disturbance resistance capacity change with the different back zone. And so we have to make a specific management plan for each back zone. So, and then we also found a low to moderate positive correlationship between biotech and abiotic disturbance resistance capacity. So this is a kind of a key message that we identify that by implementing effective forest management plans, and through this we can manipulate the stand structure that can further foster and development of the emerging properties that can enhance the overall resilience and the ecosystem productivity. So this is the part one, and now I am moving to the part two. That is just focusing on a drought and the future drought resistance capacity. So the first thing is, why is matter to study the future drought resistance. So again, I put this figure here. We can see what is happening if we see the RCP 8.5, so from 2011 to 2040, and how we go onward. So we see that the precipitation amount is decreasing, specifically in BC. So it's with, and we also have a, the global warming and the climate effect that have an impact on drought severity and the duration. And we have seen this in the past as well in terms of heat wave in BC. And these drought are the current drought and the projected drought have a significant impact or could have a significant impact on a tree health and also the carbon sequestration and the timber supply in BC. So it is very important to evaluate the current drought resistance and also how it will, change across the time. And so how we can do it to, or how we can calculate the future drought resistance. So to do this one, we have to use a kind of any simulation model that actually give us the future projection of the growth our stand, and then based on that projection growth, we will able to quantify the drought resistance. So in this case, we are using FCS, and FES also have a PC version. In the next few slides, I will explain how FES is working. So FES BC actually is adopted from FES US version, so the Northern Idaho. So in USA, they have a specific version for each state. And then FES BC is actually from the FES NI. So they adopted in 1994. It's is already calibrated for a few zone like ESSF, IDF, and ICH. We also did some kind of a calibration in SBS when we run it, because we have a multiple inventory data from the PSP plot. So we check that multiple inventory data, basal area, and the other stand attribute. And then we also cross check with the FVS, how FVS is doing with the same data set with the same interval. And there is also like a work in progress to calibrate the all the the SBS and SBPS zone and subzone and all their variant. And on the right side, you can see a figure of a stand that I run in FVS in 2020, and then in 2020, how it looks like in terms of basal area, and also the species, and how it different, and how FVS is actually running on this specific stand. So how actually FVS is work? So we actually, so it's have a kind of a web version. We can open that one. We can input a Excel file there, and that Excel file actually have a three sheet. So the first one, the most important, is the individual tree data set. The second sheet is with the stand level data set. So in the individual tree data set, we have all the stand individual tree there. There we have their DBH. We have a tree number there. We have a species there. So FVS BCD, it recognizes almost all the species that we have in BC. So we put in individual tree data set, and the stand level data set have a stand kind of a name, and then we can also manipulate what would be the maximum basal area, or what would be the maximum growth in that specific back zone. So that is something like with the site index, species, and the back zone. And then we can also add there a different event that is in term of thinning, that is in term of regeneration, that is in term of any kind of harvesting events there. So we can manipulate FVS in each cycle run, like for each run. So 1 year could be a one cycle run, 10 year could be a one cycle run. So we have their flexibility there, but we can add a different, the management events there, and FVS will follow all this management event, and it's give us a output. So it's give us technically a lot of output, but the important output that is I use in this study, that is the individual tree data set output. So we have individual tree data set in like all the tree DBH, also their per hectare factor, and all other, their age is there. And then I have a stand level data set that have the stand basal area, stand mean age, and all these, the relevant attributes there. If we want to add a kind of a, the more cycle here, or if we want to add a more kind of the thinning or something there. So it will go back to the cycle like a step 2 and then follow the step 3. That is the output. So all the plots of with the individual tree data set is simulated from 2020 to 21 century. And then we add a seedling number there after each 20 year, subalpine for 300, spruce 200, lodgepole pine 100, Douglas for 100. And these seedling actually distributed in the plot based on the proportional basal area of each species. So the 300 mean does not mean that it will add a 300. For example, if that plot have a 50% subalpine for, so it will add up 150 seedling after each 20 year. And yeah, it's proportional basal area. So the next step is when we have output from the FVS, the individual tree dataset output. So we use this drought risk assessment tool. I explained it a little bit before. It's based on AT and PET, and it's have a 3 time period, 1 time period from 2020 to 2040, second from 2050 to 2070, third from 2080 to 21 century. The resilience score that is actually in the drought risk assessment tool is the risk score is based on the back zone. Like we have SBS, ESSF is the variant. In this example, we have like here DW. So the D means that relative precipitation, that is D is dry, and the W is the relative temperature, that is warm. And then we have a one that is site series, like how much that site have a capacity to grow the vegetation community. And then we have a 7 RSMR classes from 1 to 7. 1 is the driest and the 7 is the most wet site. RMS class, because we don't have a RSMR class for all the PSP plot, so we are doing all further analysis on class 3 and 4. Like class 3 is relatively driest to class 4. Okay, so this is the graph actually how these species is their resilience is allotted and how it's changing across the time. So you can see at the top is the back zone, like, and the variant and the side series like ESSF DK1, and then we have ICH DW1 and SBS DW1. Then we have a species, we have BL, that is subalpine fir, we have a Douglas fir, lodgepole pine, and then we have a spruce that is SX. So you can see that what the resilience is 2020, the next period is from 2050 to 2070, and then the last period is from 28 to 21 century. So based on the AT and PT value, that is actually linked with all these climate model and the projected climate. As the AT and PT ratio is changed, the species resilience score is also changed. So this is show that how and it's changed with the back zone variant and the side series. And how we actually add how we integrate this drought risk assessment tool in our FVS-BC individual tree data set. So it's go with the species, is go with the back zone, sub back zone, and the side series of that species, is go with the RSMR class, like we are using the class 3 and 4, and it also go with the time period. So we have a, for example, FVS BC output in 2020. So we will put there based on the species back zone, sub back zone, series RSMR class 2020 value. That is, for example, in ESSF DK1 for BL for all the species that is one. So it will go one there. And then based on this individual tree kind of a resilience score, we do a aggregate at the plot level, and that aggregate actually based on the basal area weightage. So for example, if a plot have a 80% subalpine fir and the 20% lodgepole pine, so when we make an aggregate at the plot level, so the 80% from this aggregate is coming from subalpine fir and the 20% is coming lodgepole pine. So this aggregate is actually based on the proportional basal area of the species in the plot. And this is just a heat map, just a very, look from the top, how resilience is changing in our different back zone across the time. And also we have the RSMR class 3 and then RSMR class 4. 3 is relatively driest than 4. So there is a change, and we can see especially in the SBS, if we see in the RSMR class 3, so there is a change in 2050, and then there is also a change in 2080. So like a dark blue mean that high resilience, light blue mean that low resilience. ICS is also changing, and I think there is a prominent change in ESSF and ICH. So this is a just a heat map for all the plots. Those are located in these specific back zones. And this is a bar plot, like how the resilience is actually distributed of all for each plot. So we can see that so one is the maximum, zero is the minimum. So if we see a comparison between the classes, as I mentioned that the RSMR class 4 is a kind of a more width comparatively to 3. So we have a almost all the plat have a, especially in the SBS, they have a high resilience in class 4 in 2030. I am just showing here a 3 time period, 2030, 2060, and 2090. And then there is a kind of a long and a huge fluctuation in the ESSF and in the class 3, but again with the class 4 ESSF showing a comparatively high resilience in 2030 and also in 2060. The other thing that we can see here and also highlighting in the next slide is the resilience is changing. So in 2030, it was a kind of a high resilience. More of the plot was like above 0.75, or the medium value is above. And then with the time, the medium value in the plot distribution is going toward a zero, that is a lowest. And this change is more prominent in SPS, especially in RSMR class 3. So this is the change in resilience. So how is calculated? So the 2020 is a base year, and then we have a difference between 2020, 2030, 2020, 2040, and onward until 21st century. And in 2030, we don't see much difference in a resilience like there is what we will see in the 2020. But in 2060, we see a difference. And almost I would say that most of the plot, maybe the 90% plot, especially in the SBS, is they are lowering their resilience. And this scenario is more, the prominent in 2090. So it showed that with the time, on the temporal scale, the drought resilience is decreasing. And this is something also alarming for us to make us some, the management plan to enhance these resilience. And this is a kind of a one example how we can modify the potential drought resilience or the projected drought resilience. So this is a figure for us for all the plots. Those have a subalpine for basal area more than 50%. And then we have a here you can see a four color, the red one and the orange one. So those are the less than 0.5, and the green one is above 0.75, like high resilient. And then we have a yellow one that is kind of above 0.5 but less than 0.75. So the plots those have a more than 50% subalpine for basal area. Their resilience is is prominently changing and is decreasing from 2020 to 21st century. Like we can see a lot of the red here that was before the orange, and that was before the yellow that is turning to red. So this is one way how we can modify our stand. We can reduce the subalpine fire, we can plant with large pole pine, we can plant with the broadleaf, and then we can increase the overall drought resilience for the stand. So what is the next step? So the next step is that to perform a different silviculture treatment, and we, for example, performing in 2030 and reducing the basal area to 10 meter square, 15 meter square, 20 meter, and 25 meter square for all the stand, and then see that how it's have an impact on a projected resilience. And then we can, as I showed you in the last slide, how a different species is important. So target a different species removal and then planting with a drought resilient species, and then see that how it's have an impact on a future projected drought resilience. And then also evaluate which kind of a thinning uh, uh, practice treatment have a positive and the long-term impact on our future drought resilience. A kind of a summary here, FVS BC can be used for growth projection in interior, and the southern BC is more calibrated for the southern backzone. Projected drought resilience of PGTSC, PSP plot are decreasing at a time temporal scale. Change and decrease in projected drought resilience might different in a different backzone, and that will helpful to us to make, as I mentioned, our backzone specific management planning. And then we can also evaluate here that forest management could be used as a tool to increase the projected drought resilience. So you are welcome to ask a question, and if you want to reach to us for a further to know about our research, so you are welcome to contact us.
Thank you, Sohail. That was a great presentation. Before we proceed to answer the questions, let's take a moment to fill out a post-webinar survey. So I'm going to launch it now. So there are 2 questions in total. You may need to scroll down to see the second question.
It is the question.
No, I
Okay.
mean the second
Okay.
question for the
Survey.
post-webinar survey.
Okay.
I think at this moment I haven't seen any questions. I'm not sure if people are still typing their questions. Let's give them a few minutes. Well, if there are no questions at this moment, I would like to bring this session to a close. Sohail, I saw you already have your email address in the slides. So if anyone has any questions in the future, please feel free to email Sohail. And thank you all for participating in our CIF electronic lectures. And once again, thank you very much to Sohail for the great presentation. Bye, everyone.
Thank you.